Thank you so much for the introduction and for hosting us all here today. It's been a great time so far. So yeah, as you said, my name is Taylor Patti. I'm from NVIDIA, and don't let the NVIDIA, affiliation fool you. I'm actually a physicist like the rest of you. I just kind of work on big quantum problems there, which is the topic of today's talk. So I'm going to talk to you guys about, large data collection that we could do on large quantum systems. How can we really efficiently go study systems at scale and do so in interesting ways? And then how can I train classical AI models to make valuable inference on quantum systems for all different sorts of applications? So to maybe be a little bit more specific here, what we're going to talk about in the big data category, we're going to talk about an algorithm that I'll be presenting at Supercomputing in a month from now, which is pre-trajectory sampling with batch execution. So this is just a way of gleaning a lot of useful data from noisy quantum systems, a lot more than we could before, orders and orders of magnitude more. And next, for the smart models category, for the AI models category, we're going to talk about all sorts of different applications of Fourier neural operators. So I'm going to introduce those, and then we're going to kind of speed date mine and my collaborators' research on Fourier neural operators. And then finally, if time allows, I want to philosophize a little bit with you on the last slide, talking about in terms of like the greater picture, where I view this branch of research going and what I'm interested in terms of this research. What sorts of qualities do I look for in a research problem when I think that we can really tackle it with GPUs, AI, big compute, and the intersection of all these things. Okay, so let's get started with this pre-trajectory sampling with batch execution topic. So basically it'll come as no surprise to anybody here that, in addition to coherent quantum systems being miserable to model, right? I'm going to talk in qubits today, I'm sorry, I know that's a little bit too popular of a term, two-level quantum system, whatever. I'm just going to say qubit. But we know that they scale like 2 to the n different floats to generally describe a quantum system that's coherent. But we know that describing a quantum system that's incoherent, right, that's noisy, is even worse. You now generally need a density matrix, which is like 2 to the 2n, and that's just terrible. So for this reason, all sorts of physicists and computer scientists have come up with great approximations that you can use to better approximate these sorts of systems. And one such methodology is called the trajectories formalism. It has some qualitative kind of similarities to the stochastic wave function if you're more familiar with that. But we'll look at the trajectories formalism today because that's what pre-trajectory sampling with batch execution extends. So what you basically do, instead of building a full density matrix, you say that's way too much work, that's way too big, you instead stochastically sample errors from your quantum space. And then those stochastic sets of errors, from each of those, you build one quantum state. Now you have an ensemble of m such quantum states, and the statistics of that ensemble should approach that of your density matrix if m is large enough. And m might need to be very large, but as long as it's larger than this terrible pathological 2 to the n, you're going to be in good shape, and you're going to rather use this method. So that's the kind of benefit to this. So we were using this method for various applications in physics, so one in particular that I'll get to on the next slide. And we liked it, but we had we had a wish list of basically 3 things. So the first was that we wanted to be able to obtain a lot more shots, a lot more quantum measurements from each state preparation. We weren't satisfied with just one, and that's what these vanilla implementation trajectory methods have always done. Number 2 is we wanted to be able to fine-tune our models, so we wanted to be able to fine-tune our control over what areas of the state space we were sampling. We wanted to maybe target the most likely error sets. So we wanted to maybe target error sets that included 2 qubit gates or something like that. And number 3 is we wanted to retain this valuable metadata that is what errors actually occurred. In trajectories methods, what you would usually do is you'd throw away the information about what error this shot corresponded to, what sets of errors this shot corresponded to. We wanted to keep that because we say, okay, this is training labels, right? We like that. So to give you guys a little bit more of a concretized picture here, this is what we were working on at the time when we developed this, an ML decoder for quantum error correction. So quantum error correction, I have my noisy qubits, and I say, okay, I'm going to measure some syndromes from this, and someone should be able to tell me how to correct this, right? So if I have a bit flip and a phase flip, bit flip on qubit 0 and a phase flip on qubit 2 here, right? Someone should be able to tell me, based on the syndromes, what I have to do to correct these things. So the idea of an ML decoder, an AI decoder, is that you're going to pass in those syndromes, and then it's going to say, oh, okay, flip that first bit back, and that second bit fix its phase, and it better do it well, because if it doesn't do well, I'm going to end up with an even a worse off state. So that's kind of it's an interesting research idea that a lot of folks are pursuing in different ways these days, and so we are pursuing it as well. And now I think when you keep this in mind, you can understand why we had the wish list of 3 things that we had. So why do we want more data? Because these AI models are super data hungry. I mean, if you look at AlphaQubit, for instance, like the Google paper that worked on this, they had billions and billions of shots, right? This is a really data hungry process. So you better be able to glean this very effectively and efficiently. Why do we want to be able to target specific errors in our space? Well, because sometimes you need to fine tune a model. Like any large model, you need to be able to fine tune it. You need to say it's not performing well enough on this, or I want to specialize it for these types of applications, for these types of errors in this case. And then finally, what was this error information that we don't want to throw away? Well, this is those training labels. We want to do supervised learning whenever we can. We don't want to do unsupervised learning if we don't have to. So these became training labels. So now that you know what we do and why we're doing it, why don't we talk about the how and actually kind of look at a large-scale overview of pre-trajectory sampling and batch execution. So this is really broken into two parts. There's the pre-trajectory sampling part and the batch execution part. So for the pre-trajectory sampling part, you just define your noisy quantum system as you'd have to define it to simulate it in any old way. And you're going to choose one of our mini sampling algorithms. So there's different things that you could target in sampling. You could, for instance, sample totally probabilistically, but just in a way that's going to be more efficient and give you more data. You could sample the most likely errors. You could sample all sorts of different things that I've kind of gone over them already, right? Certain kinds of errors, certain regions of error space, it's whatever you want to do. So you just need to choose a sampling algorithm that's designed for that. We have various. So out of that sampling algorithm, it's going to consume this noisy quantum circuit, and it's going to give you two things. It's going to give you, first of all, your sets of errors, the one that you've requested, you know, if they're the most common ones, they'll be the most common ones, so on and so forth. And it's going to give you the number of quantum shots. So this would be the number of different bit strings you want to measure or any other expectation value you want to measure from that. So depending on what you want to target, the number of bit strings will be different. If you just want to gather a lot of data, then a million measurements for each one of these. And if you want to keep it proportional, then your more likely error sets will have more measurements. So that's the pre-trajectory sampling part. This is all very simple. This is all like polynomial time stuff to do. It's really straightforward, but it gives you ahead of time a lot of information about your system. It gives you ahead of time the errors that you want to do. And it puts you in a position where you can now calculate basically an extreme amount of samples, right? You can get a lot of data by saving intermediates. And so the intermediate saving part, your computational intermediates is what I'm saying, the intermediates of computation, is going to come into play in your accelerated simulator. So you're going to plug in your errors that you want to do and the number of shots you want to collect for each of those into your accelerated simulator. This could be state vector. This could be tensor network. This could be an extended Clifford simulator. This could be a couple of grad students with an abacus. It could be whatever you like, but you just have to adapt each time you have to adapt your methodology each time to fit these and to make better use of the intermediate. So with each new platform, it becomes a more and more interesting engineering problem each time. So what we've done so far and what we'll show in this paper is state vector and tensor network. So, but regardless of how you run it, this problem is deeply parallelizable. It's embarrassingly parallelizable. So you might as well run it on a big, of course, I at NVIDIA am going to run it, as should you, on some very large multi-GPU, multi-node, mega cluster supercomputer, and it will scale to as many GPUs as you have, because each of these trajectories is going to be completely parallelizable. It's a completely independent run. And built into basically your jailbroken simulator that's going to accept these arguments that came out of the pre-sampling part is going to be the maximal use of intermediates. So in your state vector case, that's going to be building the state vector once and then sampling from it many times rather than rebuilding it every time in the very foolish way that kind of other implementations, not foolish, but right in the very kind of rote way that other implementations have done. In the tensor network case, it's going to be kind of a lot more exotic of a process. It involves saving contraction paths, adapting contraction paths. It involves partial contractions, conditional sampling, all these sorts of things. It's really as far as you want to push it. But this framework allows you to push it that way. And in so doing, you put all these elements together and you could gather a truly massive data set. So we were able to get, for a 35-qubit color code that had enough T-gates that it wasn't suitable for any kind of near Clifford simulation, we were able to get 1 trillion shots in just 2,000 hours GPU hours, which 2,000 GPU hours on a cluster is really not that much at all. And then for the tensor network, we were able to do the same with a similar but like larger distance code for 85 qubits. We were able to get 1 million shots in just 1,000 GPU hours, and we haven't even fully kind of worked out the bugs on that implementation yet. I'll get to that in a couple slides. So this is a really powerful technique that folks should be using in general when they do large data collection for noisy quantum systems. And I just really want to bring home with this graphic here, I think this graphic might help me illustrate 2 points I want to make. Number one is how simple this process really is. Like, it's not some big complicated thing. I came up with it, and I'm a very simple woman. It's not complicated. And the other thing is it's not niche. It's very, very general. And so to prove to you guys how simple this is and how general it is and how you should probably almost always be doing it if you're doing any kind of trajectory simulation, I want to just break it down pictorially. So what I have here, the circuit that's on the right is, your left, my right. So the circuit that's on your left is basically just some sort of an example circuit. Green gates, I've done coherent gates to be green, and I put them as solid because solid is going to imply they're definitely going to happen, right? This is a deterministic gate. And then the blue gates, these are noise operators, and I made them hollow because we're modeling that they're kind of probabilistic, right? In the trajectories formalism, we say that they may or may not happen. That's how we model them. So typically what you would do with any other kind of trajectory simulator is you'd go through this gate by gate, you would apply the coherent ones, you would basically draw Monte Carlo style, a random float, and see if you apply the noisy ones. And then once you got to the end of that circuit, building that exponentially hard state vector tensor network, whatever it is, you would sample once, and then you'd throw those intermediates away, you'd throw your state away, you'd throw all the information about your errors away, and you would move on. But what we say is actually quite simple and quite generally useful. Let's first sample ahead of time. I have some example samples over there on the right. Blue is now filled in because these noise gates have been chosen to be deterministic now. They're definitely going to happen for this trajectory. You keep these, you have all this information going forward, and you can recalculate a lot of different expectation values and other kind of interesting pieces of information from each trajectory that you apply. Okay, so let's just look at some of the performance data from this. So I'm going to start with that 35 qubit color code with T gates, and then I'll also talk about on the state vector, and then I'll also talk about the tensor network one after this. So we were really fortunate in that the state vector implementation of the simulator we wanted to work with, CUDA-Q or CUDA Quantum, which is NVIDIA's state vector simulator. It's very fast. Everybody should use it. It's very nice. It's a very mature implementation. So it had all the bells and whistles we needed to adapt it to do this work. We didn't have to look too far or settle for less, really. And so here on the x-axis is the total number of shots that we got from each error preparation. And here on the y-axis is the shots per second. And both these axes are logarithmic. So you can see that we got an enormous amount of speed up, like over 1 million times, just by getting more shots. And the reason why you get it basically your number of shots, your speed up proportional to your number of shots, is because the complexity of building such a quantum state is exponential, but the complexity of sampling from it is only polynomial. So basically, once you have that state, you might as well sample as many times as you like, because there's the extra cost involved in doing so is totally negligible. The complexity is just so much smaller. Also, you might ask yourself, well, do I really want that many shots? And if you're going to treat a decoder, yes, you would. So if you look on the other axis, the blue one here, you see the proportion of unique shots. Just for 35 qubits, all the way up to 100,000 shots, you're basically never seeing a shot that you've seen before. They're almost all unique. Even at 1 million, half of them are brand new. So if you want more data, unique data, to train your decoder on, if we think we should train decoders in this way, then you're definitely going to want to use this kind of sampling algorithm so you get as many unique shots as possible. And you might as well give yourself 1 million times more data. That's how you get to a 1 trillion shot data corpus to train your AI model. I also want to take a second to just look at this tensor network implementation as well. This is for 85 qubits. So the tensor network implementation has a lot of potential. In fact, it probably has even more potential to allow us to explore large systems and to allow us to really accelerate our data acquisition. However, you're not going to see it yet in this graph, not because it doesn't have said potential, but because the CUDA-Q tensor network implementation didn't have all the bells and whistles we needed yet. We still have to kind of break parts of it and put them back together, so it's going to allow us the flexibility to reuse these intermediates and the flexibility to really do the full extent of this algorithm. We're actively working on that now, so expect to hear some news in the next few months, some paper out there where we've shown that we get, not only 1 million times speed up, but 1 billion times speed up or something great like that. No exaggeration. But in this early implementation that we had to finish on a very short time budget, we only got to like 40x speed up, which 40x speed up is pretty good. I'm proud of our little sensor network, but there's a lot further we can push this through kind of always intelligent reuse of intermediates, computational intermediates. And so you guys will be seeing that shortly if you keep your eye on the literature of this stuff. Okay, so that completes the big data portion of this talk. So I'll move on to I'll move on to the AI part of this. So I said I'm going to talk about one model, and then we're going to kind of like speed date my research for various quantum applications on that, the research I do with my collaborators. So the model I want to talk about is the Fourier neural operator. So all this is kind of pioneered by the Anna and Kumar group at Caltech, our dear collaborators there. And so neural operators, maybe I'll start there for folks who might be unfamiliar. A neural operator is a lot like a neural network, except for it doesn't have a fixed resolution. So a neural network maps one vector space of a given size onto another vector space of a different given size, right? But this is always fixed. A neural operator is very flexible. It can handle all sorts of different resolutions. So if you think about, say, processing images, a neural network would need to have a single resolution of image, both in height and in width, right? A neural network would need to have that, and if it didn't, it would have to conform the image by downsampling or upsampling, basically changing this to fit the structure in which it knows how to process. A neural operator can take now an image of any resolution. It can take more pixels, it can take fewer pixels. It's built in to its design that it can handle things of different size, of different resolutions, as long as we're still talking about the same basic function, as long as it's doing the same basic work. So a Fourier neural operator, as you might imagine, is a neural operator that makes use of the Fourier transform, the fast Fourier transform. And this is really useful for physics because it's really useful for differential equation, right? We know that Fourier transforms are a great way to do analysis and processing on differential equations. So what we basically do is we endow this neural operator with the power of Fourier transforms, allow it to learn in the Fourier space, and now it becomes very good at learning differential equations and learning how to generalize those and apply those. It basically learns the differential operator. So here's what that architecture looks like here. The beginning of it, can I use my mouse? Would that work? Yeah, it lives. Okay, the beginning of it looks like a lot like a typical neural network. It's just, some input goes into some, highly connected layer. The output looks similarly, some highly connected layer. All these things are parameterized. These are all learned parameters. It leads to some output. But in the middle here, we're going to do some magical stuff, and that's the Fourier layer. You have many of these. So each Fourier layer bifurcates. So you pass the first part, you basically copy your data. You pass the first copy of your data through, again, just like another very traditional, fully connected neural layer, ancient deep learning stuff, the things you've seen a billion times here. But the other part of the layer, you're going to pass through a fast Fourier transform. You're going to truncate some of these higher frequency modes. You're going to pass this now through a parameterized layer. This is just this kind of same kind of matrix multiplication that we know and love, where we learn parameters, that typical ML stuff. With the secret sauce being that you're now learning on the Fourier transform stuff. So this is kind of the secret sauce of the Fourier neural operator, are these R matrices right here, where I now get to learn parameters on my Fourier space, on my frequency space, if you want to call it that, right? And that's going to help me learn these differential equations. That's going to help me learn the change. And then I do an inverse Fourier transform, get back to my original space, combine these two answers, and pass it off to the next Fourier layer. So this is like the intuition. This is the architecture that allows you to learn these differential equations. So many times the Fourier neural operator had already been deployed on classical problems. So this is like a turbulent flow problem where they all of a sudden take some initial condition and they start driving it. And so basically what you do is you pass in your initial conditions, here's two different cases, you do the computation to learn the ground truth, and then the Fourier neural operator, if it's trained, could do these amazing predictions where it totally knows how the system's going to change. There's a lot, and you might say, well, why would I want to why would I want to train a Fourier neural operator to be able to do this stuff? Why wouldn't I just do all the simulations in the way that we've always done them, right, with supercomputers? And there's several reasons, but there's two that are relevant to quantum systems, and so those are the ones I'm gonna bring up now. The first thing that's really cool about Fourier neural operators, I'm gonna say FNOs because it's a lot to say. I'm getting really tired of talking. So the first thing that's really cool about FNOs is that you can reapply them. So like, let's say you only ever train your FNO from time 0 to some time t. Well, that's fine. If I want to go from t to 2t, as long as I've trained it well, I can go ahead and reapply it. If I want to go to 10t, I could apply it 8 more times, and then I can go to 10t, and without ever having to strictly learn these later times, as long as I've learned the operator well. Because the whole idea is I'm actually learning that time evolution operator. So that's the first good thing. The second good thing about them is they're really fast. They're way faster than doing this integration once you've trained it. It could easily be millions of times faster. And so when I have something that's a million or millions of times faster, that's a horse of a different color, right? It's not only a quantitative difference in what I can do, it's a qualitative difference in the types of problems that I could even begin to approach, or the types of approaches I could use to even target certain applications. So these are kind of the two big benefits of the Fourier neural operator. Okay, so now let's talk about a few physics problems that we did with this. So the first physics problem we did with this is that we just applied it to random spin models. We said, okay, random spin models, not a lot of structure here. I don't want to give it some nice structured problem. I want to really make it work. I want to give it one of the most difficult things I can think of, some random quantum model, and let's see how it does. So the short answer is it did pretty well, as long as you train it well. So in both of these figures, the x-axis is going to be time, the y-axis is going to be fidelity. The white regions is the performance of the FNO on times that it has seen before, right? So this is the actual training data we're giving it. And the shaded regions are going to be its performance in regions it's never seen before. So that's times we did not train it on, that it's just extrapolating to, because remember, again, it has this amazing ability to extrapolate to later times. So this first graph, it basically tells you that if you do purple and dashed is good. You get really good fidelity, and everything else you get badly. So the difference between purple and green here is random versus low energy. So it's basically just saying you want to feed these things random quantum states, because then they will learn a huge part of the Hilbert space all at once, whereas low energy quantum states, you'd have to evolve it for longer, therefore providing more training time, a more complex training process to get it to learn the same things. So basically, yeah, give it random quantum states, show it as much of the Hilbert space as you can afford to, so that it can learn the Hilbert space, because that's what it's really doing, is learning this unitary evolution. And then dashed is better than solid, dashed being FNOs that have seen multiple different time intervals, so just a few different slices of how things could look, and solid would be those who have only seen one time interval. So this is basically, first graph here is just saying it works. I mean, look at the fidelity on dash purple, right? Look at the fidelity on a random state that's trained with various time intervals. It really is a super valuable method. You just have to train it right. For the second plot, it's very similar, except for now we're comparing a couple different FNO implementations to UNets. So UNets are convolutional neural networks, which are also really cool, right? But the thing is that they basically memorize, right? They memorize things, they learn how to memorize and generalize, whereas FNOs are actually learning the differential equation operator. So UNet falls apart as soon as we get into the shaded. UNet falls apart as soon as it gets to times it hasn't seen before, because it's learned to memorize. It hasn't learned the differential operator. Whereas FNOs still do really well. You can see that fidelity is still hanging out at unity up there, because it's actually learned how this time evolution works, rather than just trying to memorize something. And because if you memorize something, you can't just necessarily extrapolate into the future. Yes?
Does it learn the differential operator, or does it learn like a short time evolution operator?
In this case, it actually learns the solution to the differential equation. So basically, it learns the unitary. It learns how to propagate it further in time. But yeah, but whatever the solution at hand is, obviously, like for classical problems, it's going to learn the classical solution to the dynamics. So this was the first problem we did, and we were quite impressed with how well it did. And so now I'll kind of move on to some of the other projects that have perhaps spun out of this. So the first one's actually the most recent. We're just getting started with it now. It came from a collaborator of ours, a student in the Neurong lab at UCLA, who was reading our paper. This is actually his slides here. He was reading our paper, and he read what we wrote about using tensor networks to kind of couple this ability of the neural operator to extrapolate to later times. So what we said in this paper was, hey, we should train these things with neural networks. We should train these things with tensor networks, because we know that tensor networks, you can have a wider and wider tensor network for only polynomial cost, but a deeper and deeper tensor network, that has exponential cost. So the idea is this: get a big old tensor network. You want to do a big old quantum system, and a very large, challenging, you couldn't do it with state vector. Maybe you don't have a big enough quantum device yet, so on and so forth, right? Get such a tensor network. Now train it to time t, where t is the deepest, is like the longest time that you could do such a deep tensor network. Now you're really pushing up against the limit of your computation, whatever that is. If it's a big supercomputing cluster, then you're filling the big supercomputing cluster, right? Because of that. You're only getting to time t, that's as far as you can go. The tensor network can't go past that. Now use a FNO, use that data from that deep tensor network to train your FNO from time 0 to time t. We know that we can reapply the FNO many times now, though, right? So we can apply it to 2t. Now we can take t to 2t or 2t to 10t. We can apply it many times. And this is our idea, this is our hope. We're going to try this with various quantum systems, like a 2D Fermi Hubbard model has been proposed as a good example. Our hope is that what we can do is we can basically now probe quantum spaces that we could never reach before, right? Because we have something that we can only, the deepest tensor network that we could muster was only going to get to t. Can we get to 2t? Can we double basically the amount of computational power in this? Because the FNO has learned the structure from this very computationally intensive tensor network that we can now artificially push forward with a Fourier neuronal operator in a way that we couldn't just add more layers to the tensor network because it wouldn't fit in memory, even a very ambitious kind of NV-linked memory. So that's the idea here, and we're going to apply some physical systems of structure, probably the 2D Fermi Hubbard model, because it has nice applications and it has nice structure, and we think that because it has this nice structure, we could actually glean something from it in a more compact way. I'll talk a little bit more about that philosophy at the very end here. Another project that we're doing here that's totally kind of quite different, also with the Neuron Lab, is using FNOs to design quantum control sequences. So in this case, what we're doing is we're doing this for molecules. So basically, I can train an FNO not only to tell me the time evolution of some input state, I can also train it to give me the time evolution of some input state based on different parameters I give it. So in this case, control parameters, the frequencies or the detunings of my optical system, right? Maybe the laser intensities, things like this. I can choose to put those in as inputs as well and have the FNO learn to generalize that. And then what it will do is it will give me the time evolution of my system, which you see here. And if I have the time evolution of my system, then I know how things work. Now, what if I want to design a better control sequence? The point of what we can do then is we could use the FNO for inverse design. So I can say, I don't know what control sequence I should use. I just want to tell you what my input state has to be, and I want to tell you the output state that I know that I want. Now, AI model, tell me the control sequence I need to use. So, here's where I want to end up. FNO can now be used to help you get there. So how you do that is you train your FNO, now it's a surrogate model. It'll basically take your input plus your parameters, and it'll get you to the output because you've trained it that way. But remember I said that the FNO is like millions of times faster than doing the typical integration that we would normally do. So now I have something that's millions of times faster. I could do all sorts of really sophisticated inverse design. Well, I could also do stupid inverse design that's still really powerful because I can do a million shots now for the time of a single shot, right? So I could just search my space if I want to do that. But I could also have like a secondary AI model that's kind of supervising the task. I do gradient descent on that. There's all different ways I can do inverse design. When I have such a nice tool like an FNO that allows me to do things a million times faster, now the world's my oyster, and I can do a lot of great different inverse design, including inverse design of pull sequences for hopefully interesting quantum information protocols. And then finally, the last piece of research I want to talk about today is with our collaborators in the RS group at Oxford. So they build quantum dots out of silicon germanium. And this is a really challenging process. So here's what their quantum dots look like with an SEM, with an electron microscope. But to build one of these things is a several-step process. First of all, you have to guess an image of the gates. This is basically the substrate that they deposit or scrape away. You have to guess what image of the gates you would want to build a quantum dot set that you would like. Then you have to do these calculations with Maxwell's equations to see what your potential would look like, and then you have to adjust these. And this is, you're adjusting these like, oh, I think it should look like this to give me the quantum dots that I want. And then once you have this, you have to do the Thomas Fermi approximation. So all these are kind of computationally intensive simulations that you'd have to do to finally get your hole density or your carrier density or whatever kind of density you want to use to describe your quantum dot. Now the issue is, first of all, that this is all really computationally intensive, but also that it's really hard to look at some gate sets and to think of some voltages that you would apply and to be able to guess the kinds of quantum dots that you're going to get. Like I know the kind of quantum dots that I want, but I don't know how to get there. And so we're using the FNO again here to do this inverse design. And again, we're empowered to do so by the fact that this is like millions of times faster with an FNO once you train it. So all I have to do is train it, and now I can do some truly ornate and sophisticated AI inference in reverse, right? Allowing me to reverse engineer these systems through inverse design. And this is actually how we build GPUs now. This is a lot of how the most sophisticated methodology for building GPUs now works, is through inverse design. Gone are the days where we kind of, started here and thought forward and guessed and checked and computed as best we could. Now we start here and we go backwards. And so I think it'd be really great to bring in quantum dot technology up to this same kind of point of sophistication of design and really enable us to scale those. It's certainly done a lot of good for us in classical hardware. Okay, so with this, I just want to take a couple minutes and kind of like recap and think about maybe a little bit of the greater picture here. So to recap, we talked about some examples of using big data sets of big quantum systems with pre-trajectory sampling and batch execution. We also talked about training AI models to do inference that's useful to us on quantum systems. Hopefully you found those applications useful too. But I think I just want to take talk about a little bit of the greater picture that I see for these sorts of projects and why I'm interested and when I'm interested. And if you guys ever have any projects that overlap with us, feel free to come see me, and maybe we at NVIDIA can help a little bit in compute or in algorithmic know-how or AI know-how or something. So the why, I think, and I think I speak for a lot of people at NVIDIA when I say this, the why we're interested in these things is because we want to push the limit of what we can study. Like that's all that we ever do here, right? And AI is clearly the tool of right now to do this. But when do I personally see that we can make a huge impact in how well we can study the things that we'd like to study? Are problems that are that have one of these two qualities. So the first one was what you saw in the big data collection, and that's when we have a problem that teaches us, when we have a research project that teaches us to evade some self-imposed complexity. Quantum systems are complex, right? To even build that state vector is 2 to the n. It's exponential complexity. Nothing I can do about that. But in a lot of the different approximations that we work with, there's a lot we can do about that. So, right, in PTSBE, we saw that we were taking so many places where we had extra information to learn from, or when we had intermediates that already existed, and we were recomputing them, right? We were recomputing all these intermediates, doing this work millions more times than we actually need to do. We need to learn to evade that self-complexity. Or we were throwing away that information about errors. That takes away the information that we're already blessed to have in the system. We need to evade that self-imposed complexity of doing things dogmatically, doing things because this is the way that we've learned them. So if you ever think that you have a problem where there's some self-imposed complexity and there are computational intermediates that we could take advantage of, that's something I think I'm very interested in, and I think that the folks at NVIDIA are very interested in it as well. And this goes especially for the AI portion. I'm really interested in projects that capture some sort of a sneaky structure, right? When I say this problem's really hard, I think I need 1 million parameters to learn this. In fact, maybe I need 1 billion parameters to learn this, but I don't think that I need 2 to the n parameters to learn this. I think I need a little less than 2 to the n parameters to learn this at scale, because I think that there's some structure to it. Those are the sorts of quantum problems that I think we should be addressing with AI. So if you ever need any help with any of those, I think that me or someone else at NVIDIA could really put a dent in that as well. And with that, I thank you for your attention and open the floor to any questions.
That's all right. So I'm very interested in the FNO specifically as it applies to kind of replacing these really dense, kind of overly complex brute force convolutional neural networks. What are I guess my question is whether you use an FNO or an NO, like just regular neural operator, how do you decide that? Because I would assume that the FNO also has problems dealing with like non-periodic data or data that doesn't experience the same frequency, like when you're dealing with something that UNet can deal with, like image processing or like fire detection, flood detection, things like that. So I know that's a little outside of the realm of this talk, but I am kind of curious what you think.
No, it's a great question. So when to use an FNO and when to use a different NO, when to use a different neural operator, really depends on your task. I think you really gotta have great insight there when you talked about the periodic aspects of the Fourier transform, right? Exactly, right? When we learn something that we're going to be able to kind of coherently put together on some sort of a time scale, that's when the FNO is very powerful. For other problems, though, there are many other neural operators. There are neural operators that are going to exist that haven't existed yet. You can make a neural operator in your own image, whatever your favorite function is, whatever your favorite functionality is. ML really is just like a black box at the end of the day with some intuition. But yeah, problems that have periodicity, including pseudo-periodicity, including very long periodicity, I've been very impressed with the FNO for.
I also want to better understand the FNO So are you seeking to solve real-time quantum dynamics, bunches, or what are you seeking to solve there?
Yeah, so there we did real time. We also did spatial things, right? We did basically Maxwell's equations plus the Thomas Fermi approximation. We haven't done any imaginary time evolution yet, but that's not to say that we couldn't. It's a pattern learner. It learns basically it learns differential equations. It's a differential equation learner. So if you have a differential equation, we could definitely take a look at it. Like it probably could.
The reason why I'm asking is because oftentimes with real-time quantum dynamics, there isn't a great pattern.
Yeah.
And so there are complexities there. So this is something we thought about doing without quantum computers, learn the operators in C, and it seems to be messy, but maybe you guys have a handle on this.
Yeah, I'd love to chat more about it. I'd love to see the actual problem. And then, as he said, it might even be a different neural operator or a different architecture altogether. But I think for time evolution, I'm quite optimistic that as long as we correctly apply it, it should have some great potential.
For imaginary time evolution, how do you train on finite time, like training set? How do you capture long-lived dynamics that are longer than the training set time?
Well, so I can't really speak to for imaginary time evolution because I haven't done it. But in general, how would we do like long time dynamics? There are definitely going to be pathological problems where you would have to just throw in more and more compute, right? Now my T would have to be long enough for the levels that I'm looking at. So unless I have like an isolated system that only hangs out in these bands down here where it has shorter periodicity, my T has to be long enough. Like that's always the issue. Like I think if I go back a slide, here we go. Capture sneaky structure. There has to be enough structure that I'm able to learn. If it's way too long of a period and I'm not able to say extend my simulation that far, then I can't learn it because there's never any free lunch in AI. Beware of anyone who tells you that they're going to learn everything in a tractable way. Nothing ever comes for free. You have to pick the right problem that you can really hang your hat on and learn in some sort of a compact way. So there will be pathological problems for which we can't, but there are many problems in physics that are interesting for which we could.
When I think of Fourier space, there is, of course, this time picture that you've talked about, but you also mentioned this super resolution, which would be sort of the spatial view of Fourier space. So can you imagine using these Fourier neural operators to think about scaling system size, where like a lot of the phenomena that we want to study are just getting sort of super resolved in space?
100%. Let me first say that you're very quick, because I didn't say super resolution, but that's what this is called. So good. So you guessed the name. If I had like prizes or candy, I would throw you. So I think your question was basically, can I do this in other spaces? Absolutely. So like if you, here, listen to me. Okay, here we go. So like as an example here, right? Part of this is in whole space. I mean, what is the Fourier whatever of whole space? I guess it's like whole frequency. Yeah, it boggles the mind to even think about what that would be. But it's absolutely applicable to all sorts of different differential equations.
So maybe I have a question. Yeah, I think I missed this slide. When you talk about this, using this method to model devices, how does it compare with finite element solver?
That's a good question. So it is a lot of upfront work, right? But we would use something like a finite element solver. Not in this case, we don't. But in other projects I'm working on, which will not be named yet, but one day soon, part of that is finite element solving, right? So you use that to get your training data. You use it to get your ground truth. But then once you have it, it's like a million times faster, and you can do crazy stuff with it. But definitely for like a single pass, you would never train an FNO because you'd be like, I'll just use the finite element solver or whatever my appropriate pipeline is. But when you want to do a lot of it and you want to do like inverse design, you train it with something like that, and then you let it loose.
Thank you very much. Okay, thanks for your game.
Thank you guys.